polymers, plastics, plastic materials. When we think about material science, the market is always part of it. So we are designing materials for a purpose. These are human design materials. And so what purpose? Well, it varies, right? We can pay attention to hardness, to flexibility, to ductility. We might need a conducting polymer. We might really want to make a biodegradable polymer, or at the very least a recyclable polymer. We might need it to be cheap, or it might be the cost might not be a factor, right? If I'm designing a polymer for a space shuttle hull, my cost constraints are obviously different than if I'm trying to design a better trash bag, right? So lots of these design criteria come into play when I think about polymers. But the main point for this section is that those macroscopic properties come from the microscopic structure, right? So we're going to think like chemists in how we design these polymers. Again, a polymer is just a chain of small molecules one after another. Okay? So what kind of microscopic structure do we mean? Well, first we can look at the chain length, right? So the chain lengths for polymers are really, really long, right? So this is a log scale number line. And if we look at something like nylon, the optimal length for a nylon chain in terms of Daltons, right, or grams per mole, it's about 10 to 100,000 grams per mole of those chains, and they'll vary a little bit. But that's kind of the range in which nylon is both strong and flexible. And if you think about a nylon rope, then yeah, I need it to be both strong and flexible. If it gets longer, if I'm able to make very, very long chains, which there are some factors that fight against that, but those are going to be really, really strong chains and probably very heat resistant as well. But they're not going to be flexible, right? And so they might make good parts for like a combustion engine, but they're not going to make good rope. They'll probably be too expensive for rope as well. But if they're shorter, if they're like on the hundreds of grams per mole range, that's just too small for them to be act as polymers. They don't really act as chains, and they're brittle and they're pretty bad materials. They're more like crystals than plastics. We can also, speaking of crystals, we can think about morphology, right? So the big divide here is between crystalline materials and amorphous materials. In a crystalline material, all of our polymer chains are kind of regularly stacked, okay? Whereas in an amorphous material, everything is kitty-wampus, right? There's no regular arrangement of chains. They're kind of every which way. They're probably not linear. So crystalline materials are often very linear chains, whereas amorphous materials, these chains might be highly branched. And so there's really no way for them to sit. I like to think of this as a stack of logs versus a pile of brush. All right, the stack of logs is obviously going to be way stronger of material, right? And so in the material it's going to be higher melting, better mechanical strength, etc. But it's not going to be flexible. All right, I can't take a stack of logs and bend it, right? Whereas here, my amorphous, this is not going to be a strong material, right? I can't build a house out of a pile of brush, but it is going to be flexible, right? I can deform it, I can bend it, and so I have flexibility here. So again, these are often my two antipodes when it comes to polymer design, strength or flexibility. You often have to sacrifice on one to get the other. A very good material, you could imagine, could combine these two, right? What if a material had crystalline segments and amorphous segments, right? Then it would be really strong and really flexible. So nature has examples of such a thing. So spider silk is a great example of a heterogeneous morphology. So there are segments of spider silk where the peptides that make it up are very regular and held together by hydrogen bonding. And there are other parts of spider silk that are amorphous, that don't have that regular order. And that is why silk is so strong and yet so flexible. Right? If you've ever walked into a spider web, A, ew, B, think about how thin that spider web is, right? That's much thinner than the human hair. And then think about how much that spider web gave, right? How stretchy it was before it finally snapped, right? And then as you kind of walk back, spitting out spider web, right? That web went back to its original shape. So spider webs are incredibly strong given their cross section, given their volume. And so it's a really amazing material. If we could be able to design a factory to make spider silk strands the size of my finger, we could build suspension bridges from it. That would be an amazing material. So far, we've had a hard time doing that, right? So we can, as far as we've got, we've engineered goats to express spider silk in milk, which, good job, biology, I suppose. Nice. The point is that it's an unsolved problem. We'd really like to be able to engineer materials that combine some ordered sections that give us strength with some disordered sections that give us flexibility. Spandex is one example of that we'll come to in a little bit. How do we tell how long the chains are? Right? We can't exactly put this through our GCMS because we can't boil a polymer. And so how are we going to get the molecular weight? Well, what we're going to use is something called size exclusion chromatography, or SEC. So the idea behind SEC is it's a column, kind of like the chromatography columns you did with spinach last term. Only instead of just silica, our beads in there are going to have lots of different pore sizes, some big pores and some little pores. And then we're going to put our polymer solution through it, a polymer dissolved in something. Right? We're going to assume that our chains are kind of rolling up into kind of perfectly spherical balls. And so we're going to draw a linear relationship between the length of the, or at least draw a direct relationship between the length of the chain and the size of the spherical little ball as it comes through here. Okay. So the idea is that you can kind of picture little polymer balls and big polymer balls coming in here. The little ones are going to find more nooks and crannies to fit into. And so it's going to take the little ones longer to get through this column. The big ones are just going to kind of like plow through, right? It's kind of like, if I brought my son to a museum, I would be like, ooh, what's this? Ooh, what's that? Check out this exit sign. Look how red. And Owen would just be like walking right through, not stopping, right? In that case, he would be the bigger chain. I would be the tiny little chain. Yeah, okay. All right, so again, what we get is a plot kind of like this where we look by elution time and see sort of how many or what signal we have coming out, so how many chains are coming off. And we usually have some polymer standards where we can say, okay, I know that 20,000 comes off here and 30,000 comes off here, and so forth. So we can actually use standards to get our number. This plot also tells us about polydispersity. So polydispersity basically tells us the range of chain lengths we see in our sample, right? You can imagine maybe we have a perfect polymerization technique where every chain is precisely the same length. That would be called monodisperse, right? Most of our methods are not monodisperse. There's a little bit of spread in shorter and longer chains, and sort of the cheaper the material, then usually the broader that range. And as you can tell, from a mechanical standpoint, a narrower range is good because we have a better handle on exactly what the properties of the material are.